All right, today we are going to go over section 4.6, which is about congruence in overlapping triangles. Now, this whole section is sort of what I would consider to be the wrap-up or the culmination of everything we've looked at this chapter coming together. And that means that the diagrams we're going to see in this section are probably the most complex, as well as the examples being the most complex that we've seen so far. So please make sure that you have a set of highlighters or a couple of highlighters in there to help you outline the triangles that we're looking at and kind of really give yourself ways to identify the different pieces that are congruent. So that's actually the first part we're going to do. We're going to identify corresponding parts in triangles. And you've sort of been doing this the entire chapter. If you had two triangles that were congruent, you could pick out which angles and which triangles were congruent. But you haven't done it a whole bunch when the triangles are overlapping. So here we have triangle FHJ, right? So let me get a smaller thing here. So triangle FHJ is going to be right here. And we also have triangle KHG, which is this triangle. And in this example, all we're doing is we're identifying the corresponding parts of these two triangles. So we already kind of know from the context of this question that these two triangles are congruent. So all I need to do is pick out the side lengths that are the same and the angle measures that are the same. For example, the short side of the green triangle is HJ. That's got to be congruent to the short side of the purple triangle, which is HG. The smallest angle in the green triangle is angle. I'm going to use three letters, HFJ, right? That's this angle right here. And the smallest angle in the purple triangle is angle HKG, right? That's this angle right here. So pause this video for a minute and write down the other two pairs of corresponding sides and the other two pairs of corresponding angles. All right, so additional sides here, we should have that FH is congruent to KH, and we should have FJ is congruent, that's not a J, sorry, FJ is congruent to GK. As far as our as far as our angles go, we should have angle FJH congruent to angle KGH. And we should have angle FHJ congruent to angle KHG. So that's going to represent all of the corresponding pieces. Notice that this last one, that's the same angle in both triangles. That's this angle in the purple triangle and this angle in the green triangle. So here's how we're going to do things today. We want to show that certain triangles are congruent. And using those triangle congruences, we're going to tell whether certain pieces are congruent. So these are our CP-CTC problems. Once I find out that the triangles are congruent, I can use CP-CTC to find out that angle EGD, that's this one right here, is congruent to EFH. So one of my questions is, what triangles should I use from this diagram to show that those are congruent? And in my opinion, since I know EGD is one of the angles that I need, then I'm going to use the triangle I make with that angle, which is triangle EGD. And then the other angle EFH is this angle right here. So I'm going to make the triangle I make with that angle. So my first goal here is going to be talking about these two triangles being congruent. And how do I know? Well, I notice automatically that DE and EH are congruent. So I'm going to start with that. DE is congruent to EH, right? And that's given because that's already in the diagram. What else do I notice? I notice that at the base of this triangle, I can tell that this piece right here, DF, and HG are congruent. But DF is not the entire side length of the blue triangle. And HG is not the entire side length of the orange triangle. But take a look at this one in the middle, right? FG is going to be the same whether it's part of the blue triangle or part of the red triangle. So I know that DFG is going to be the same length as HGF, because when I add these two pieces, it'll be the same as adding these two pieces. That is our segment addition postulate. I can say that DG, that blue side, is congruent to FH because those pieces added together are congruent. So that's the segment addition postulate. All right. After that, we're going to go ahead and say, well, what else do I know here? This last one can be a little tricky. This last one is going to require us looking at the entire triangle, DEH. Because when I look at the entire triangle, DEH, I notice that it's an isosceles triangle. DE and EH are congruent. And since it's an isosceles triangle, I can say, wait a minute, if these two sides are congruent, then their angles in those corners, angle D and angle H, must be congruent as well, because that's the isosceles triangle theorem. So I can bring into my reasoning here that angle D has to be congruent to angle H because of the isosceles triangle theorem. Once I do that, I notice, hey, I have 3 congruence pieces. So once I have 3 congruent pieces, I should be able to say that my triangles are congruent. So I come over here and I'm like, well, if I look at just the blue triangle, I'm going to figure out the pattern of congruence. I have a side, I have an angle that's included, because then I have another congruent side marked over here. So these 2 triangles must be congruent by side, angle, side. And again, it's really important that I'm naming these triangles correctly. So maybe if my first one is triangle DEG, take a moment and decide what the name of the second triangle should be. If you said triangle HEF, you are correct. And that was by side, angle, side. But that's not what the question was asking. The question was asking, is angle EGD congruent to angle EFH? Well, now that I know the triangles those angles came from are congruent, then I know those angles have to be congruent because corresponding parts of congruent triangles are congruent because of CPCTC. So when we answer this question, we can say yes, because of CPCTC. Or I could add that underneath as part of my reasoning in my little proof thing right here. All right. Let's keep going. I'm going to check to see if I'm still recording because it would be really unfortunate if I was not. Cool, I am. Okay. So in the next example, I want to do a very similar thing. I want to find out whether VW and YZ are congruent. And I'm going to use some things about triangles and some congruent triangles to decide whether those side lengths are congruent. So I have a couple of options in terms of what triangle I want to make that has WV in it and what triangle I want to make that has YZ in it. I think I'm going to go for, and you could do this differently. Oops, that's not a highlighter. I'm going to go for this triangle right here because ZY is part of that triangle. And then this triangle right here that has WV as a part of it. And the reason I'm going to do that is the first thing that stuck out to me is that VZ is the base of both triangles. So I was like, oh, automatically I know VZ in the red triangle has to be congruent to VZ in the yellow triangle, right? So I'm going to go ahead and say VZ is congruent to VZ. Remember, the reason for that is the reflexive property. And I can go ahead and I can mark that with a congruence mark. The next thing I'm thinking is, wait a minute, take a look at this little angle in the corner of the yellow triangle, angle YVZ. And take a look at this little angle in the corner of the red triangle, angle WZV. Those are marked with one arc each. So those are congruent to us. That's a given. So angle, remember 3 letters for this one because it could be multiple angles with their vertex at V. So angle YVZ is congruent to angle WZV. That was marked on there. That was given. And I noticed that there are some other markings on here as well, giving me these other above angles. But this angle with 2 arcs, that's outside of the yellow triangle. And it's not a whole entire angle in the red triangle. Same with this one. This is outside the red triangle, and it's not a whole entire angle in the yellow triangle. But I do know that they're congruent pieces. And right next to them, there's some other congruent pieces. And so it would stand to reason, right? If I added an angle with 1 arc and an angle with 2 arcs, becomes this entire angle, it would be congruent to an angle with 1 arc and an angle with 2 arcs over here, added together. And of course it is. That is called the angle addition postulate. We're going to bring that back from earlier. So we can go ahead and say that the entire angle on the left, angle WVZ, is congruent to the angle on the right corner, angle YZV. So again, notice that those are slightly different than the ones up above it. And of course, that's because of the angle addition postulate. So I add 2 smaller angles that I know are congruent to 2 other smaller angles, then my resulting angles are going to be congruent to one another. And now when I look at these, I can kind of make these a little bit darker if I want to. So I've got that, I've got my 2's. Now I have, if I just look at my red triangle, 1 angle, an included side, and my other little angle that are congruent. So that must mean that these triangles are congruent by angle, side, angle. So once again, naming these correctly means naming them in a certain order. If I call the first one angle WZV, then what's the name of the second one? Go ahead and figure that out. Hopefully you said angle YVZ. And that is, of course, by angle, side, angle congruence. But remember, that's not what the question asked. The question asked whether VW and ZY are congruent. Well, now VW is one side of the red triangle and ZY is one side of the yellow triangle. And so we know they must be the same because they are pieces of congruent triangles. So finally, we can end this question by saying that VW is congruent to ZY by, you guessed it, CPCTC. All right? And again, these are pretty long, but you're looking for things every time. So you're looking for 3 congruencies, right? I had 3 congruencies here. so I could use my theorems. Let's keep going. Like I said, these are a little bit long. Oh, it looks like I've got some overlaps that are kind of weird here. Let me break this into a couple of different sections. There we go. So here I have a more complex diagram, but in this case, I've been given the triangles that I want to prove congruent. So that's kind of nice because I don't have to figure out which triangles I'm trying to prove to be congruent. I can just highlight the ones in the question. So I want to prove that triangle BFE, go ahead and highlight triangle BFE, is congruent to triangle CEF. So we've got to think about ways that those two triangles would end up being congruent, right? And so I kind of see right away, I see that they have that same thing where they have a shared base. So side FE has got to be the same in both triangles. And that jumps out at me first. So I'm going to write FE is congruent to FE because of the reflexive property. And I'll go ahead and put my marks on there. It looks like I'm going to need to use 3 hash marks because I've already used 1 and 2. And when I look at where those first and second hash marks are used, something jumps out at me here. I see a side angle side pattern. And I'm like, wait a minute. If this is a side angle side pattern, that means this triangle right here, triangle BAF, that's got to be congruent to triangle CDE over here just by side angle side. So I've got triangle, we'll call this one BAF, is congruent to triangle CDE, and that's just marked already as side angle side congruence. So those outside triangles are congruent. And each of those outside triangles includes one side of the triangles we're looking for. So BF is part of triangle BAF, and CE is part of triangle CDE. So we can say we now know that BF and CE have to be the same. We'll go ahead and do that. So we'll say, okay, I know that BF, that side length, is congruent to BE. Not BE, I'm sorry, CE, that side length, by CPCTC. Those are corresponding parts of the triangles we just showed to be congruent. Guess maybe I need 4 hash marks on them. Right, so now I've got 2 sides of the green triangle congruent to 2 sides of the blue triangle. And I gotta keep going, I gotta keep thinking about what I can do here. And there's a few ways I can go about this. You might see some stuff already. But, let's see. I do notice I already knew that this angle BFA and this angle CED, they must be congruent because they're part of triangles that are congruent. And if they're congruent, they each make a linear pair with an angle that's part of the triangle I'm looking for. So angle BFA makes a linear pair with angle BFE, which is part of the triangle I'm looking for. And angle CED makes a linear pair with CEF, which is part of the triangle I'm looking for. So both of these are supplementary. Both of the interior angles are supplementary to the same angle out here. So that means BFE and CEF have to be the same, okay? I think I'm going to do that in 2 steps because I got to talk about that these angles are the same first by CPCTC. That's got to be part of my problem. So angle BFA must be congruent to angle CED by CPCTC. They're part of those outside triangles I proved to be congruent. And since they are congruent, I know that these 2 inside angles that are that are supplementary to congruent angles, they must be congruent as well. So angle BFE is congruent to angle CED And I think when we first studied that, we called that the supplementary to the same angle theorem. They're supplementary to the same angle. And when I look now, I have 3 congruencies in my green triangle and in my blue triangle, right? I know that, where are we at here? FE is congruent to FE, BF is congruent to CE, and BFE is congruent to CEF. Remember this piece? These are not angles in our triangle, so they don't count there. But with my 3 pieces, I can notice that I, looking at the green triangle, have side, included angle, side. So side angle, side congruence. Triangle, BFE. I'm just taking these from up here so I know they'll be written correctly. Is congruent to triangle CEF by side angle, side congruence. So prove those triangles are congruent. We just proved those triangles are congruent. Few more examples here. Again, this section is just really full of examples. We can do lots of different problems with overlapping triangles that can help us to understand these theorems a little bit better. So here I've got 2 more triangles that I want to show to be congruent. I want triangle ACD. So I'll go ahead and outline triangle ACD to be congruent to triangle ECB. So those are my 2 triangles in this problem. Let's think about what we already know and what's marked out here. I first notice I've got some congruent angles, and they happen to be 1 angle of the purple triangle and 1 angle of the green triangle. So angle A, I can say that because it's the only angle with vertex A, is congruent to angle E. That's been given. What else do I see here? Ooh, C. There's a clue. Take a look at this angle up here. Angle C is one of the angles in our purple triangle. But also, angle C is one of the angles in our green triangle. So angle C has to be congruent to itself. It's in both triangles, so it's got to be one of our congruencies. So angle C is congruent to angle C. That's our reflexive property. I can go ahead and mark it on my diagram with 2 arcs, even though it only exists in one spot. That's okay. That angle is congruent to itself. And I do notice some side congruences on here, but I noticed that there's not a whole side, right? CB and CD are congruent. But, ooh, actually, they are, because CD is the short side and CB is the short side. So let me go ahead and use those, okay? So CB is congruent to CD. That was given. So let me make some darker marks on my triangles to show my congruent pieces. So that's congruent. There's a congruent side. So if I'm just looking at my purple triangle, then I know that I have an angle here. I have an angle here. Remember, this is not part of the purple triangle. It's not the whole thing. Angle here, and a side right here. So these 2 triangles must be congruent by angle, angle, side. So triangle ACD. Again, I'm copying up there from the problem prompt. Triangle ECB by, what did we say? We said, I think, angle, angle, side. There are definitely other ways to prove that these 2 triangles were congruent. I actually, on my example paper, have a side angle side proof. We could do that as well. So there's not just one way. There's oftentimes enough moving parts on here that there are a lot of ways to show that these triangles can be congruent. Number 11 is interesting because I've got these 2 triangles and I've got I've got a diagram with a ton of marks on it. So let's see what that does for us. We want to show that NQM is congruent to PMQ. So when I look at these, I'm looking for congruency theorems, and first thing I see is that these are right triangles. And I'm thinking, ooh, we learned a right triangle theorem. We learned hypotenuse leg. So let's see if these have hypotenuses and legs. It looks like my hypotenuse has 2 pieces with hash marks, and so does this one, so they're congruent. I have this leg with 2 hash marks and this leg that's 2 hash marks. So these could be congruent by hypotenuse leg. But that's not all, right? I look at the shared side and I say, well, what other sides are congruent? The shared side, the vertical sides, and the hypotenuses are congruent. So this could be side, side, side congruent. But then I'm thinking, wait, my right angle is an angle I know. And I have this side at the bottom, and I have this angle, and I have this side vertically. So I have an included angle. Same thing on my blue triangle. So I actually have side, angle, side congruence as well. So one diagram can actually show quite a few different things. If I went even deeper, there's probably a way to finagle some angle sides in here as well. And actually, I do see that right away. I see that triangle MRQ is isosceles. And since MRQ is isosceles, that means that it's got 2 angles that are the same in its little corners right here. And since those angles are the same, now, if I'm looking at my red triangle, I've got an angle, I've got an angle, and I've got a side congruent, as well as an angle, a side, and a right angle congruent. So I can also use angle, side, angle, and I can use angle, angle, side. There's all kinds of ways that I can show that these 2 triangles are congruent. I think that's all of our triangle congruence theorems that could work here, which is crazy, okay? Last one, separating overlapping triangles. I've got to run these 3 bus routes, and I can draw a separate triangle for each of them because I can just draw where they go. So I'll draw my purple route in here. Oops, I want my highlighter. There we go, purple route. I'm just following the stops. Actually, I'm following the little colored icons on the map. And then I've got my green route. And I've got my red route. Okay. And the question here is, are any of the routes the same length? Right? Well, we can use what we know to figure out that they're the same length. I'm going to take a look because I can see already that my purple one is bigger, but my green one and my red one could be the same. So I'm actually going to redraw those over here, okay? It's not going to be perfect, but it's as close as I'm going to get. So there's my green route. And that's my red route. I can't read colors, what? That's what my red route looks like. And then I'm going to trace the shape of my green route as well. What am I doing with the colors? Your guess is as good as mine. All right, so there's my green route, which apparently is not closed. There we go. Okay. So I know that each of these are right triangles. I'm going to go ahead and draw in those right angles there because they are in my diagram. And what else do I know? I know that in my green route, I've got pieces that are 2.1 and 1.4 on this side. I know I've got a 1.2 and I've got a 0.9 on this side, and I'm just copying these over. And then for my red route, I have a 2.1 and I have a, 1.2, 0.9, 1.1, and 0.3. So all together on my green route, this piece is 2.1 units long, the same as the short red side. And all together on my green route, the hypotenuse is 2.1 plus 1.4, that's 3.5 units long. 1.2 plus 0.9 plus 1.1 plus 0.3, that's also 3.5 units long. So that means that, hey, I've got right triangles with hypotenuses and a leg each congruent. So these two triangles are congruent by hypotenuse leg. All right. I would say the most important stuff in this section is really these first 4 examples where we were giving proofs or reasons why those triangles were congruent. That's what I want you to focus on the most in this section. Sorry for the long video. This is a lot to talk about, but now you can go ahead and try these in your practice.